Okay, so this is going to be Unit 1, Lesson 2. We're going to be talking about slopes of tangents, and we'll be looking at limit stuff. Just going to again make sure my pencil, right thickness, there we go. All right, so we talked about in the previous lesson what limits were. They're used to describe the value or output that a function or sequence approaches. So the input is going somewhere. The purpose of a limit is to tell us what the output is doing. So we could look at a limit of a sequence. So let's take a look at this particular one. Here's this sequence here, 1/2 to 2/3 to 3/4. If we're just going to head out to infinity on this sequence, what would happen? What's the limit of this sequence? Again, if you need time to pause, I'm going to suggest you can pause the video at any point in time. I'm just going to move forward. So moving forward, what would come next would be 4/5, right? We just got a arithmetic sequence in both the numerator and denominator. This one, 1, 2, 3, and then 4, 5, and this one is one more, 2, 3, 4, 5, 6, right? And so in general, what would the nth term be? Well, the nth term should be n over n plus 1. Notice how the denominator is one more than the numerator. And let's say by the time we got out to, 1,000, this would be 1,000 over 1,001. And so we can see, I hope you can see that now we're getting closer and closer to 1. We're going to be close to 1, but small. So as the sequence, let's say as n goes to infinity, then we're going to say that n over n plus 1, so that's our input. The input is going to infinity. The output, which is n over n plus 1, is heading toward 1, but I'm going to write negatively because it's going to be a little bit smaller than 1 because the denominator is larger than the numerator. What will happen with this one? What value is this approaching? So as x goes to 3, what's happening to our output? And that, in this particular case, that's the output. And again, you can be in control of the timing. I'm just going to move forward. So what I'm going to do here is I'm going to factor this. So x squared minus 9 factors into x minus 3 times x plus 3 all over x minus 3. I mean, you could put in 3.01, 3.001, and so on. We see why we can't directly put 3 in because 3 minus 3 is 0 and division by 0 is undefined. So you could put those values in. Alternately, what I'm going to show you is I could factor, and then what I'm going to note is that this function is the same as this one, x plus 3. And then I'm going to note that x cannot be 3 because this function would be defined for all numbers, and it's clear in this particular function that x can't be 3. So those do cancel out. We're left with x plus 3, and as long as I write x is not 3, this function here is identical to this one, and I now can see as x goes to 3 that x plus 3 goes to 6. I'm going to turn that down. All right, so limits can be explored around a single input or at plus or minus infinity. So here's a limit where we are sending the input to infinity. X is going to infinity, and we're wondering what this output is doing. Where's that output going? It turns out, we'll more on this later in this course, that this particular limit is heading toward 4. So limits can exist. This exists, and here we are talking about sending the input to infinity. Here's where the input approaches a particular value. This limit exists. They may not exist. In this particular case, x is heading towards 0. Not sure if you remember what the graph of 1 over x looks like, but it looks like this. We've got a vertical asymptote right there, and the limit is not approaching a particular number of value the closer you get to 0. And again, here we are sending the input to a particular place 3. And in this instance, we have a break or a jump here, but more on that later. Don't worry about it if you don't understand that now. This limit doesn't exist. So these exist, these don't. Moving forward, you have seen limits already, so we don't want you to panic. You've seen them already, you just use different notation. You were looking at behavior around vertical asymptotes, and you're already also looking at end behavior. So let's take a look at this curve. This is x plus 2 over x minus 1, and you were responsible for curve sketching these in advanced functions. So we might look at what happens when you send x to infinity. So I'm going to send x to infinity, and as x goes to infinity, I can see that I'm approaching 1 from above. So the notation in advanced functions would look like this. X goes to positive infinity, y goes to 1 positively. Now, calculus, we say that same thing, but we write it differently. We use limit notation. So instead of writing x goes to infinity, we're going to write the limit. We're wondering what the limiting value as x goes to infinity is. And then in here, instead of putting y, we put our particular function in. And in this particular case, the y is represented by this expression, x plus 2 over x minus 1. So we would say the limit as x goes to infinity of x plus 2 over x minus 1 is 1 positively. We could also say the limit as x goes to infinity, we could actually just write f at x instead of the function itself, and we could say that's 1 positively. And you could send x to negative infinity, and you can see that you are approaching 1 again. So we are approaching 1, but we're below. So we would say as x goes to negative infinity, y goes to 1 negatively. That, again, noting that we are below. We're underneath 1 in the y direction. In calculus or limit notation, the limit as x goes to negative infinity, we put the function in here, is 1 negatively. This is how you write it in advanced functions. This is how we write the same thing in calculus. Vertical asymptote here. So we've got a vertical asymptote at 1 because, when is g at x, which is our denominator, 0. That happens when x is 1. So we do have a vertical asymptote there. So now we will explore two behaviors. So we're going to send x to 1 negatively, and we can see when you go to 1 negatively, i.e. you are to the left of 1, we can see we're shooting off to negative infinity. So advanced functions, x goes to 1 negatively, y goes to negative infinity. In calculus, we say the limit as x goes to 1 negatively of, and either we write the actual function in here, which I've done in this case, or we could put f at x there, is equal to negative infinity. That's how you write in advanced functions. This is how you write in calculus. We'll look at one more. As you are heading to 1 from the right, so as x goes to 1 positively from the right, we can see that this function now is shooting off. The outputs are heading toward positive infinity. So advanced functions, x goes to 1 positively, y goes to infinity, and this is how we write it in calculus notation. All right, so the purpose of this slide was don't panic. You've seen this before. Students freak out when they see this notation. It is notation for calculus, but it says the same thing that this notation said in advanced functions. All right, some definition-y type things. The word secant comes from the Latin word secare, which means to cut, and it is a line that joins 2 points on a curve. So secant to a curve will join 2 points on a curve. A tangent comes from the Latin word tangentum, which means to touch. So it is a line that just touches the curve at one point, but it doesn't intersect at that point. Now, with the exception of a stationary point of inflection, the tangent to the curve will be either above or below the curve on both sides of this point. So I'm going to show you. See the red curve here? That's not a curve. There's a red tangent line. It's tangent at the point B. Notice how when you move to the right, the curve is below. See how it's underneath? And on the left, the curve is below. As opposed to, let's take a look at this right here. That's a point of intersection. Notice to the left, the curve is above, and to the right, the curve is below. So a good way to tell is that actually a point of tangency as opposed to a point of intersection. At a point of intersection, it'll switch, going from above to below. I mean, there are some exceptions where that wouldn't be the case, but, we can try and generalize. And so which of these lines are tangents and which of these lines are secants? And again, you can control the timing. I'm just going to move forward. So the red line is tangential right there at the point B, and the purple line is tangential at the line D. Now taking a look at the green line, none of those are points of tangency. Which lines are secant? Well, the green line is entirely a secant line everywhere. The purple line is secant at G here. That's a point of intersection, and secant at F, but tangential at D. And the red line is only touching right there, so it's only a tangent line. So red can be viewed solely as a tangent, green solely as a secant, purple can be interpreted as either a tangent or a secant. Now moving forward, more definition type stuff. A tangent line will not exist at a point if the slope is dependent on whether you approach it from the right or left. So if you could get two different values for the slope of the tangent as you come from the right or left, then the tangent line won't exist. Are there points on the curves down below for which the tangent doesn't exist? So we'll start with this one. And again, you can control the timing. So start with this one. Do we have an issue with points of tangency? And it turns out we do, right here. Coming from this side, the tangent would be the line itself, right? So that's going to give one slope value. But if I approach, that's approaching from the left. If I approach from the right, I'm going to get that tangent line. So I can draw two possible tangents. This is called a corner right here, because we have two linear functions together. Two linear functions are coming together at a corner, and you can't draw a tangent at a corner. There are two possible tangents you can draw. So one with positive and one with negative correlation. So that puts us right there at 3. We can draw a tangent everywhere to this particular piecewise curve, except at the point 3. All right, so you take a look at this next one, and you think about the same kind of thing again. Is there a place where the tangent we would draw is dependent upon whether you come from the right or the left? And again, you can be in control of the timing. So moving forward. So the tangent that I draw if I come from the left is going to be right here. It's going to be a vertical line. I'm going to get the same line as I come from the right. I'm going to get a vertical line here. This is actually two root functions coming together. And because this was the vertex of a parabola, when you rotate that 90, this would be a horizontal tangent. This is going to be a vertical. So we do have a vertical line here. So we are getting the same tangent coming this way and coming that way. However, the slope of a vertical line is undefined. So we're not going to be able to find, we'll find out later, this is called the derivative. We can't actually find the slope here. The slope does not exist, although the tangent line does. This drawing that we have here, this is known as a cusp. So in this particular case, we can argue that we can draw one tangent. However, it becomes a vertical tangent, and the slope of a vertical line does not exist. All right, how about the last one? So in this particular case, we've got two possible tangent lines that we can draw. Here's this one right here, and that's the line I would draw as I'm approaching 5 from the left. And here is the green line, is the one I would draw as if I'm approaching 5 from the right. They're two different tangent lines. And so if two different tangents exist, then you can't draw a tangent at that point. And again, this is also a cusp. So you can't draw a tangent at a cusp, nor can you draw a tangent at a corner. So no tangents at corners, no tangents at cusps. A cusp is where two curves come together. A corner is where two linear functions come together, piecewise linear, like absolute value v. All right, moving forward. All right, so which of my lines here best represents the slope of the tangent at this point here, 2, -6. So which line? So we've got magenta, we've got green, we've got red. Which one gives us the best approximation for the slope of the tangent that we would draw through that point? And again, you can be in control of the timing. I'm just going to move forward. It turns out for the pink line, so we're right here in the next place we intersect the curve is right there. So this would be my delta x for the pink line. And for the green line, the next point it intersects the curve is way over here, and that would be my delta x for the green line. And notice how each of these are approximately equal. They're about 0.5. This is 1, not 0.5, it's about 0.75. So it looks like 1 and then a half of 1, and because 1 is 2, this is approximately 0.75. So it looks like delta x is 0.75 for both the magenta or the pink, I guess we could call it, in green line. So they both give equally bad approximations. Now, I hope you remember from advanced functions, a delta x is 0.75 is too large if you want to approximate the slope of a tangent. And I do believe the value we were after for delta x's was at least 0.001. Some instances we asked you to do 0.001. So that delta x is too large. But they both give a better approximation than the red, because let's take a look at red. We're going from there down to there. That's a very large delta x. So both of these are way better than the red delta x, which I've written as approximately a delta x of 6. How could you create a better approximation for the slope of the tangent? Then we, as I mentioned before, you got to make delta x as small as possible. Those delta x's are too big, so maybe we'd want to put the other point right there, and maybe we would want to draw our, so maybe I better get a line drawing tool to do that, something like that. Would give us a better approximation for the slope of the tangent. All right, given only one point, describe how it would be possible to determine the slope of the tangent at that point. How are we going to do it? Let's see if I can open this GSP sketch. All right, and then let's just start the animation. So right now, this is a very bad estimate, right? Let me see. I'm just going to pause momentarily. All right, so continue. I want to put these lines on so that we can see here. So I'm trying to find the slope of the tangent at this particular point right here. And what we can see right now is that this is a very large delta x from there to there. So how do I get a better estimate for the slope of the tangent? I make delta x smaller. And so see how we're making delta x smaller as we move the point along the curve. And the best possible estimate would be sort of this one at the very end where we've made delta x as small as possible. Erase those traces, and again, I'm going to show you again. I'm just going to highlight this line here. That's delta x. It's a very large delta x. Notice as I move this point, I'm going to pull that second point along the curve. Erase those traces. That doesn't appear to be a free-flowing point that I can drag. But again, I'll highlight this. I'm going to animate. And notice how, let's show you the tangent line now. That's the actual tangent line. And I'm interested in this. And notice how, as we make that line delta x smaller, the better the estimate we get. Make delta x smaller, and then when we got a very small delta x, which we had toward the end, that gave us the best possible estimate. So the smaller delta x, the better the estimate. All right, so coming back over here now. Now what are we going to do? So if you have a whiteboard or something at home, what I'm going to recommend you try to do is draw a curve. Maybe I'm going to walk you through on a new slide what we're doing. So get my pen. I think I'm going to do this with lines this way. So I'm going to draw a line like this, go like this. So those are my axes. I'm now going to freehand a curve. So I don't know, some kind of curve that looks like that. All right, so then I'm going to pick a point on the curve that I want to find. I'd like to draw a tangent through there. But I can't find, so I'm going to call this the point A, comma, F at A. Okay, and this is Y equals F at X. All right, so you're used to writing X, comma, Y for the coordinates of a point, but you can write X, comma, F at X, because in this case, Y is F at X. So this is any point on the curve. This is a specific point at A, comma, F at A. I can't find the slope of a line if I draw a tangent through there. Let me do it with this again. So I'm interested in the slope of the tangent line that's passing through there, but the problem is you can't find the slope of the line given only one point. So what we do is we draw a second point on the curve. Change the color right over here. And what I'm going to do is I'm shifting over h units. I called it delta x as well, but we go h for the horizontal distance. So what has happened now is the new x coordinate will now become a plus h. We were at A, but we've shifted h units to the right, so we're now at A plus h, and the y coordinate will now be f at A plus h. So instead of writing y there, I'm going to plug A plus h into that function. So the coordinates of this point are A, comma, f at A, and the coordinates of my second point are A plus h, comma, f at A plus h. Now I'm just going to take you back to this picture. So that's how I created this here. And now what I'm going to do is I have 2 points, so I can use grade 9 mathematics. Of course, grade 9 mathematics said the slope is equal to delta y over delta x. So if I want to find out the y, I will subtract the y coordinates. There's coordinate number 1. There is coordinate number 2. So that's where that's come from, f at a plus h minus f at a. Now I need to subtract the corresponding x coordinates in the same order. So I have to start with this x coordinate here, which is a plus h, and I subtract the other x coordinate, which is right there, which is a. And now a plus h minus a is just going to give me a. So now this here is the slope of a secant. It's called the difference quotient, but it will give us the slope of a secant. And the secant is going to connect 2 points on the curve. It's going to connect a, comma, f at a to a plus h, comma, f at a plus h. So again, I jumped over here just to show you how that picture was constructed, because sometimes students have trouble following that picture. Once you have that picture constructed, then what we can do is find the slope of a secant. That's going to connect the point A, f at a, to a point that is h units away from it. And again, I'm showing you off to the side. There's the rise, difference in the y coordinates. There's the run, the difference in the x coordinates. This thing is important. We're going to call that the difference quotient. So I'm going to move forward to here now. So to find the slope of the tangent, what do we do? So we've now found that this difference quotient, which is going to give me the slope of the secant, is f at a plus h minus f at a all over h. And my 2 points are h units apart. So would it make sense to you then to say, if I want to find the slope of the tangent, what I would like to do is send that horizontal distance between those 2 points to 0. So to find the slope of the tangent, that's exactly what we do. We say it's the limiting slope of the secants. And I'm going to write it this way. It's the limit as h goes to 0 of f at a plus h minus f at a all over h. And again, we won't panic, because we're going to recognize that for what it is. That's a slope calculation. It's delta y over delta x. So we simplified the denominator because we did have a plus h minus a. That just became h. So that's the slope of a secant. And if I allow the horizontal distance between those 2 points to approach 0, then I'm going to have the slope of the tangent. And of course, it's the slope of the tangent at the point a, comma, f at a. That's where the point of tangency is. All right, so moving forward, I want to try and see this in action. So find the difference quotient that we would need to use to determine the slope of the tangent at this particular point. Now remember again, the difference quotient is the slope calculation, f at a plus h minus f at a, all over h. And in this particular case, your a value is -2. So again, I probably recommend pause the video now, because this is an important skill set. This is called working from first principles. You need to be able to plug, so we would be looking at f at -2 plus h minus f at -2 all divided by h, and you would plug that into here, plug that into there, and then you'd simplify. All right, so I just wanted to get a bit of a head start because I'm kind of slow writing on the trackpad here. So f at -2 plus h. So I'm going to do -2. I'm going to plug in 2 plus h in here, -2 plus h, because it was, we're interested in the slope of the tangent at when x is, let me just write that down, when x is -2. So -2, plugging into here, -2 plus h all squared plus 7 minus, we're going to put that in square brackets, because this would be minus f at -2. So plug in -2 in there, -2 times -2 all squared plus 7. This is -2 times, if I expand this, I'll get -2 times -2, that's 4. -2 times h times 2 is -4h, squaring h is h squared. There's plus 7 minus -2 all squared is 4 times -2 is -8 plus 7. Distributing, I get to -8 plus 8h minus 2h squared plus 7 plus 8, then minus 7. I'm going to change the color quickly. I'm going to show you what would happen. So this is a bit different from the work that you did in advanced functions. What will happen now is every term that doesn't have an h will have an additive inverse. So the -8 goes with the +8, the 7 goes with the -7, and that brings me down to here. I have 8h minus 2h squared, all divided by h. Now in advanced functions, we couldn't let h be 0 because division by 0 would be undefined, but watch what happens now. 8h divided by h is just 8. And negative 2h squared divided by h is minus 2h. So now we could actually send h to 0 to find the slope of the tangent, right? This is the difference quotient we would be using. It hasn't actually asked me to find the slope of the tangent, but that's the difference quotient I would be using. And if I want the slope of the tangent, I would plug in an h of 0, and I could see that the slope of the tangent is just going to be 8. So this is called first principle work. So in this particular case, I worked with a specific case, negative 2. Down here, it wants to know, could we find the slope of the tangent to any point on the curve? So I'm going to walk you through this one. In this particular case, if I want to be able to find it anywhere, rather than plugging in an a of negative 2, I'm just going to use I'm just going to use a as a parameter. So f at a plus h, I will plug a plus h into here. I then square that. I have to multiply by negative 2. Then we're going to add 7 minus, and then I'm going to need to do f at a, so that would be negative 2 times a squared plus 7. So this guy is f at a, and this is f at a plus h. Again, expanding this little bit here, I'm going to get a squared plus 2ah plus h squared. There's the plus 7. Distributing here, I get positive 2a squared. Distributing there, I get minus 7. That takes me to this line. I'm going to distribute this. I'm going to get negative 2a squared minus 4ah minus 2h squared. I just had to get a sip of water there. So repeating, negative 2 times a squared is negative 2a squared. Negative 2 times 2ah is negative 4ah. Negative 2 times h squared is negative 2h squared. And the plus 7 plus 2a squared minus 7. Now, if you've done this right, you'll always have a check. I just want to change the color of my pen. So if you've done it correctly, any terms that don't have an h, this doesn't have an h, and it has an additive inverse. This doesn't have an h, and it has an additive inverse. That can be your check, because if that doesn't work out nice, you've done something wrong. What I'm left with are these two terms, negative 4ah minus 2h squared, and notice they're both divisible by h. So in advanced functions, you could not let that h be 0. If you did, you do division by 0 as undefined. But now they're going to divide out nicely. So negative 4ah divided by h is negative 4a. Negative 2h squared divided by h is negative 2h. And so now that difference quotient can be used to give me the slope of the tangent anywhere. Now, can I do this? Yes, I could. I could just say the limit as h goes to 0 of negative 4a minus 2h. And what will happen here is we're going to get negative 4a minus 2 times 0. And of course that would give me negative 4a. So this expression here, I'm going to write it larger, negative 4a, can be used to find the slope of the tangent at any point a, comma, f at a. And in our original example, we were looking at an a value of negative 2. So negative 4 times negative 2 would give us 8, and the slope of the tangent to this curve at negative 2, negative 1 would be 8. All right, so let's look at another example. In this particular example, what I want you to be telling me, and when I put this on the test, when I'm talking about geometric representation, I want you to tell me whether is this representing the slope of a secant or is it representing the slope of a tangent. And I'm going to put slope of above this. If I were to put this on the test or the performance task and I write geometric representation, students aren't answering it correctly. I want you to tell me whether or not it's the slope of a secant or a slope of a tangent. And then you have to do specifics. Can you tell what the function is? Can you tell what points are being connected, etc.? And again, if you want more timing, I would suggest that you pause. So right now, I'm going to note that this is a secant. It's the slope of a secant. How do I know that? Because I don't see a limit as h goes to 0 in front of it. So this is definitely a slope of a secant. I can see the slope of the secant is negative 4. And the secant is connecting 2 points on the curve. I've got 3f at 3, and I've got 5f at 5. And the horizontal distance between those 2 points is 2. So coming over here is our summary. The above is a slope calculation for secant. And as I mentioned, it connects the points 3f at 3 to the point 5f at 5. Definitely we can see the h in the bottom is 2, but I don't really need to know the h because I can see it up here as well. And the slope of the secant is sitting over here. I can see that slope is -4. All right, so let's move on to the second one. What is the second one showing us? And again, if you want more time, you can pause. I'm noting this out in front now. We're sending the horizontal distance to 0, so I now know, again, this is a slope, but this is the slope of the tangent now. And I can see that the slope of the tangent is 2. And where is the tangent drawn? Well, I'm going to look here. The tangent is drawn at the point 5f at 5. All right, so let's read the summary on this particular slide over here. The above is a slope calculation for a tangent. A tangent drawn at the point 5, f at 5. How do I know that? H is being sent to 0 right there, and I can see that the slope of that tangent is 2. So if this were a test or a performance task question, you have to tell me the slope of what? Slope of a tangent or a slope of a secant. You have to tell me if it's a secant, the 2 points that are being connected. If it's a tangent, tell me the 1 point where the tangent is being drawn through. And then you also have to tell me, if I give you a numeric value, what that slope calculation was. All right, moving forward to the next question. I'm giving you this. I'm going to let you know this is a difference quotient. Given that particular difference quotient, can you tell me what the equation was? And remember, it's f at a plus h minus f at a all over h. So f at a plus h must be 5 times the square root of 1 plus h. And then I can also tell from the other piece that f at a should be 5. So what you're going to try to decide now is what's the equation of the function. Maybe you can start first by finding a, what is a, and then find what the equation of the function is. And again, if you want more time, you can pause. I'm just going to move forward here. I've shown you what f at a plus h and f at a are. So I can now determine that that 1 is my a, so there is a. So I know that f at 1 plus h is 5 times the square root of 1 plus h. And so if I wanted to move to f at x, then I would replace the 1 plus h with x. So it looks like my function should be 5 times root x. I'm going to make sure that works out on the other piece, because then the other piece should be f at 1. F at 1 is supposed to be 5, so let's check that out. 5 times the square root of 1 does give me 5. So in this particular case, we now know that our function is 5 root x. Will the difference quotient be able to give us the slope of the tangent at x equals 5? So this difference quotient here, can it give us the slope of the tangent at x equals 5? Now, in this particular case, I've noted a couple things. One, it's not giving the slope of the tangent because it's not preceded with the limit. But if I did write the limit as h goes to 0 of 5 times the square root of 1 plus h minus 5 over h, will this be giving me the slope of the tangent at x equals 5? And of course the answer to that has to be no, because for this particular difference quotient here, we know that a is 1. A is not 5 for that difference quotient. So it's not going to be able to. So 2 reasons. One, we could say we didn't have the limit out in front of it, so it can't be the slope of the tangent without the limit out in front of it. Then when I adjusted to put the limit out in front of it, can't be x is 5 because this different quotient is only good for when I should have said a is 5. This difference quotient is only good for an a of 1. It's not good for an a of 5. All right, so let's move forward. All right, so you're given this particular function now. And again, we're going to be doing this from first principles. This is a very important skill set. Find the equation of the tangent to the curve, this curve, at the point 1, 2. Remember to find the equation, not equation, to find the equation, we've got to start with the slope. So we're going to do the limit as h goes to 0. Remember, we've got f at a plus h minus f at a all over h. And then you can just be plugging into there. And two ways you could do this. You could do plugging in an a of 1, so you could be looking at f at 1 plus h minus f at 1 all over h. Limit as h goes to 0. But this is very general, not very robust. This only works when a is 1. If you want it to be able to work, I'm not certain what questions I might ask on this test, but what if I was going to ask you for the slope of the tangent at more than one spot? They are both the same amount of work, whether you do 1 plus h, or if you decide, I'm going to generalize, I'm going to call it f at x plus h minus f at x all over h. Because this one will be able to give me the slope anywhere. So this one gives the slope for any a. This one will only work when a is 1. So I'm going to suggest, why don't you try this on a general case, set it up, get your x plus h, plug it into here, plug it into here. You've already got your f at x. Simplify, expand and simplify. If you've done it correctly, any terms that do not have an h will have an additive inverse. They will drop out and you should be left with only terms involving h. Again, I'm going to move forward, but I'm going to suggest you should actually pause if you haven't tried this yourself. This is a very important skill set in calculus. Can I plug into this difference quotient here, simplify it, and then send h to 0 so I can get the slope of the tangent? All right, so moving forward. So again, I said I'm going to prefer to work with a general case. So the limit as h goes to 0 of f at x plus h minus f at x all over h. And let's do this a bit at a time. X squared. That's this little bit there. Minus 3x. So I'm looking at f at x plus h. There is the squared part. There is that part. There's the plus 4. And then we're going to do minus f at x. Maybe I'll change the color. So minus f at x. There's minus f at x. I'm going to expand this now. This is going to become x squared, x times h times 2 plus 2xh plus h squared. Distribute here, minus 3x minus 3h. There's the plus 4. I'll distribute here, negative x squared. Negative times a negative becomes plus 3x. Negative times the positive 4 is negative 4. Now, as I mentioned, if we've done this correctly, that doesn't have an h, so it should have an additive inverse, which it does. That has an h, it's okay. That has an h, it's okay. This should have an additive inverse because it doesn't have an h, which it does there. That should have an additive inverse, which it does. So again, if you've done this correctly, terms that don't have an h as a factor will have their opposite or their additive inverses, and then they will all cancel out in terms of adding zeros to my sum. So that leaves me with 2xh minus 3h plus h squared all over h. When I divide everything by h, I will get 2x, divide that by h, minus 3, divide that last term by h, I get h. So when you simplify this quotient, we're left with the limit as h goes to 0 of 2x minus 3 plus h. And when you send h to 0, you will get 2x minus 3 plus 0, which gives you 2x minus 3. Now, what's special about this thing here, 2x minus 3? It will give us the slope of the tangent at any point x, f at x. So this expression will give us the slope of the tangent anywhere. Now, we want the slope of the tangent at the point when x is 1. So the slope of the tangent at 1, 2 would be equal to 2 times 1 minus 3. We're plugging right into 2x minus 3. That gives us negative 1. So the slope of the tangent is negative 1. Now, we're going to be using this quite often because it's faster. I know in grade 9, when you wanted to find the equation of a line, you'd want the y-intercept. What you would then do is you would plug in the slope and a known point on the curve, and you would isolate that for the y-intercept. I'm going to show you a slightly different approach. Notice how that if I isolate this, I do y minus y naught over x minus x naught. That would be the slope. And that makes sense to me because if you take x and y or any point, a general point on the curve, any point on the curve, this is a specific point on the curve. But if you make a slope calculation by joining any 2 points on the curve, you will get the slope back. So this equation here is the one we're going to use in calculus because it's faster, and it's called the point slope form equation of a line. The things you need to plug in are, I'll change my color here. I need to plug in the known point, so and of course that would be the point of tangency. So the y-coordinate of the point of tangency, the x-coordinate, we're going to plug in the slope there. So y minus 2, that's the y-coordinate of the point of tangency, is equal to the slope we found to be -1. So negative, and then we do x minus x naught. Well, the x-coordinate of the point of tangency is 1. So in point slope form, y minus 2 equals negative times x minus 1. If you are so inclined and you do want to write it in slope y-intercept form, because that's the form you're used to from grade 9, distribute, you get negative x plus 1, bring the 2 over plus 2, so y equals negative x plus 3. This is in slope y-intercept form, and this one is in point slope form. Now, I have talked to a lot of students who've come to visit me from having gone to university and volunteers who've come in and helped in the class, and they've all given me the same message. It is perfectly fine to leave it in this form in university, and I usually talk about time being your enemy in university. Why waste time going to there? It's going to be much faster to plug into here than it is to find the y-intercept and then writing it in that form. So my advice, let's write it in that form. All right, one last question left for today. Here's a sort of a thinking question. Find the coordinates of the point on the curve that is parallel to this. So this is a parabola. So let's kind of draw a parabola. And then you've got this line 8x. Say it looks like this. At some point, this is going to be parallel to a point of tangency. So what we're actually trying to find is when the slope is where the slope of the tangent would be 8. So I'm going to suggest sort of set this up the same way we did before. We're going to have to look at, if I want to find the slope, really I'm going to write, I want to know where the slope of the tangent is 8. So I'm going to be doing the limit as h goes to 0. Now in this particular case, because we have no idea where that's going to occur, we do have to work this general case, f at x plus h minus f at x, all divided by h. We don't know what the x value is. If you prefer, you could write an a in there. We don't know the a or the x value where the tangent is going to have a slope of 8. So what we're going to have to do is work in a general case. So we do need a parameter or a variable there. So set that up, figure this out first, simplify that difference quotient. Remember, you're plugging into here, and then you can solve that equation. Again, if you want some more time to work through this, I'm sort of going to suggest you pause and you control the timing. I'm just going to move forward. All right, so as I mentioned on the previous slide, the first thing I want to do is I need a general equation to find the slope of the tangent anywhere. And I did mention that I want to know where the slope of the tangent is 8. So I'm just going to start with this little bit here. So we want 3x squared. So f at x plus h. There is this component right there. Then I want minus 4 times x. That's that component there. So if we're going to do f at x plus h, plugging in an x plus h into here gives me this, and plugging it into there gives me that. Minus, there's our f at x. And now I'm going to need to expand. If we expand x plus h all squared, we'll get x squared plus 2xh plus h squared. I should have mentioned earlier, this would be an example of something I would consider to be a thinking question. And then when I distribute this, I'm going to get, there's the 3x squared. There is 3 times 2. There's the 6xh. And 3 times h squared, there's the 3h squared. Distributing this one, we get minus 4x minus 4h. And distributing here, we get minus 3x squared plus 4x. I'm going to change the color of my pen. And as I mentioned before, that doesn't have an h, so it will have an additive inverse. That doesn't have an h, it has an additive inverse. All of the pieces that are left do have h's, so they'll be fine. If you have a piece that doesn't have an h factor, and it doesn't have an additive inverse, that tells you you've done something wrong. You should go back and check your work. So 6xh minus 4h plus 3h squared, and I've written them in this order. The terms that still have the variable x go first, and then I'm increasing the exponents for h. When we divide this expression by h, we will get 6x minus 4 plus 3h, and the h is gone. And again, the problem in advanced functions was you couldn't let h be 0 because you'd be dividing by 0. But the beauty in calculus is in this difference quotient, the h always cancels out if you've done your work correctly. So that gets us down to here, to this expression. The difference quotient, now simplified, has become the limit as h goes to 0 of 6x minus 4 plus 3h. And if you allow h to be 0, 3 times 0 is 0, you're just going to be left with this, 6x minus 4. So this will give me the slope of the tangent anywhere. So this is the slope of the tangent. At any x. And then just reminding you, in this particular question, we're trying to figure out for what x value the slope of the tangent would be 8. So in fact, what I want to figure out is when this expression, which is the slope of the tangent, when would that be equal to 8? Because I want the slope to be 8. So if I solve 8 equals 6x plus 4, I will get 12 is equal to 6x, so x is 2. So the slope of the tangent says the coordinates of the point, so I'm not done, right? So the x-coordinate is 2. Let's find the y-coordinate. That's going to be 3 times 2 squared minus 4 times 2. And that's 12 minus 8, which is 4. So at the point 2, comma 4, just double checking. 2 times 2 is 4 times 3 is 12. 12 minus 8 is 4, yes. So it wanted the coordinates of the point where the slope of the tangent is 8, and that is happening at the point 2, comma 4. All right, that brings us to the end of lesson 2. Big idea in lesson 2 is that you are comfortable working with this kind of expression. You can simplify a difference quotient. Here I have plugged into a polynomial. It would be useful for you to be able to plug those into rationals when you're looking at the homework, and useful for you to be able to plug these into radical expressions as well. Probably there'll be a post online showing you examples of each of these. So that brings us to the end of lesson 2. All right, hopefully you're finding these videos to be useful.